Hello guys, this is codeNcode and this is the sixth lecture of this number theory series, and in this lecture we are going to study about matrix exponentiation. So what is matrix exponentiation? So matrix exponentiation is basically you are given a matrix and you have to calculate its power raised to some integer. So in this example it is a raised to power n. So the normal time complexity, if you do this, would be m cube raised to m cube into n, and the reason is m, first of all, m is the dimension of matrix. Suppose a is a square matrix and m is its dimension. So when you multiply two square matrix together, then the complexity is actually n cube, and since we have to make n multiplication, so the overall complexity would be m cube into n. If we optimize this code, we can do the same thing in m cube into log n time. As you can see, it is a very big improvisation over the time complexity. The first one, that is the noise approach or brute force approach, would require m cube into n time for calculating a raised to power n, while the second method that we are going to study, that is exponentiation by squaring or binary exponentiation, that is that would improvise the time complexity and would make it m cube into log n. So let's start from very basic or noise approach. So if you remember how we calculate a raised to power n, where a and n are integer, basically like 2 raised to power 10,000 or something like that. For that, what we did was we initialized the result with 1 and then run a loop till n. Each time we multiplied base into the result and finally return the result. This was noise approach, which took like big O of n time. The running time was linear in n. Now why I'm showing you is that why we initialize result with 1. You can say that, okay, since we have to multiply base into result again and again to calculate base raised to power n, so result must be initialized with a number which does not affect overall the result. So if you initialize result with 2, the result would be 2 times the overall result. But if you initialize result with 1, the overall result would not be changed. The reason why we initialize result with 1, yep, the answer is correct, but 1 itself, if you see this, the operator, the multiplication operator, with each operator there is a special number or special element is defined with that operator, and that number or that element is known as identity element. So for real number multiplication, the identity element is 1. The identity element are defined as this. Suppose you have an operator like plus here, and if you take the identity element and you have some integer, say x, if you apply this operator with integer x alongside with its identity element, the result won't change. So the identity element for plus operator is 0. For minus element, for minus operator, the identity element is 0. For division operator, the identity element is 1, because if you take any integer and apply the division operator alongside with the binary, with the identity element, the element won't change. So goes for multiplication. If you think about XOR operation, 0 is the identity element for XOR operator, because if you have an integer x, you perform the XOR operator alongside with 0, which is actually the identity element of that operator, then the result is x. The result doesn't change. This is important concept, because that is why we initialize result with 1, because we are using the integer multiplication, not integer but real multiplication operator, and for multiplication operator the identity element is 1. This may sound very childish thing to study, but believe me, this is going to help us analyzing this code. So that was, let me show you again, this is to calculate a base raised to power n when base and n both are integer, basically 5 raised to power 12 or something like that. But now naive approach for matrix multiplication. MAT is not a data structure. I had to represent base. I have to show that base in this case is actually a matrix, not an integer. That is why I had to go with something that is more intuitive, or that shows that base is actually a matrix, not an integer this time. So that is why I'm representing, taking using MAT to represent that this thing is actually a matrix, not an integer. So we have to calculate this matrix raised to power n. So you see, we are having three different things here which we need to fill. First, the return time of this function. We have initialized we have taken a result, the data type of that result, and what should be the initialization value, and then each time result is multiplied with the base matrix to calculate the base raised to power n, and then we are returning the result. Now the question is, what should be the return type or data type of this result? Of course, since a matrix raised to power some integer is still a matrix, so the data type should be a matrix. Okay, so this is okay. But now with what value should we initialize result with? Now you see, since this is a matrix, we can't initialize it with 1. And one more thing, we as I have already explained why we initialize result with 1, because 1 was actually an identity element of multiplication operator. There and here, at both the places, you can say, okay, here also we are looking at a multiplication operator, and we know the identity element for the multiplication operator is 1. So we should initialize it with 1, but the problem is result is a matrix, we cannot initialize it with integer. But then you might realize, and you might have studied in secondary school that about matrices, and you might have noticed that this multiplication operator is not the normal multiplication operator. This is actually a matrix multiplication operator, and the normal multiplication operator and matrix multiplication operator both are completely different. So for this multiplication operator, there have to be a different identity element, and for matrix multiplication operator, the identity element is actually identity matrix. And if you have studied, of course you might have studied in the matrix algebra, so in secondary school, so you might know that you might have studied about identity matrix. It is a square matrix of size n cross n, where all the diagonal elements are 1 and the rest are 0. This is called identity matrix because, as already explained, an identity matrix, an identity element is the one which do not affect any element x when applied with a certain operator. So for matrix multiplication operator, the identity element is identity matrix, because if you have a matrix A and you multiply it with identity matrix of same order, then the resultant is also A. That is why we call it identity matrix. So now we would initialize result with identity matrix. So far so good. So to calculate matrix A raised to base raised to power n, we would take a matrix of same dimension as the base matrix, and we are talking about square matrix here specifically. So we would take a square matrix, of course identity matrix of order n, which would be the order of base matrix, and then we would n times we would multiply result with base and then return the result. Of course the return time of this would also be matrix MAT, sorry. So this is how we would calculate what we say base raised to power n, where base is actually a matrix. So if I show you this, because if you only talk and do not perform something, then you might not get what is going on. So let me just delete and let me show you how this works. So what we are taking is I've defined n to be 101, and let's take some array. Let's call it AR of size. We have taken two. This, let me just first finish this. We have taken two matrices. First is to take input, and first matrix is of size 100 cross 100, and the second matrix is for identity matrix. It is also of size n cross n, or 100 cross 100. So what we are doing, we are taking t test cases. In each test cases we are reading the dimension of the matrix and then n, and then we are reading the elements of the matrix. This is for loop which would run 1 to dimension, and this is also for loop which would run 1 to dimension. This is same as writing this thing. Let me show you just real quick. I plus plus, and then running inside another for loop which would also run till dimension. AR of I. So this thing is same as this thing. So instead of going for 3 or 4 line, I like to write it whole in a single line. So whenever you see this REP, which I have already defined here, it is basically a for loop which runs from 1 to n, where n this time is this, so it would run from 1 to dimension. So each time what we are doing is basically we are reading the elements of the 2D array, and after that we are calculating we are calculating the matrix AR, which is of dimension DIM, to power n, and then after that we are simply printing the matrix with which is having this dimension. So till now we have done nothing. Simply we have read dimension and n, and then also taken the input. After that we are calculating power and printing the matrix. So important thing is that define this function. Let's call this matrix A. What is this? This matrix A, this is dimension, and this is power, to which we have to calculate a raised to power n. Now you might see the return type is void because the result itself would be in this AR, so we don't have to actually return. We can, since AR is defined globally, so we can access it anywhere. Now we have to calculate this a raised to power n, and you might be thinking why I have also pass, or I've taken n inside this bracket, because when you are passing a 2D matrix inside a function call, you have to tell the number of columns, so of that 2D matrix. That is why, otherwise if you would simply remove this and compile this, you are going to get error, as you can see here. Declaration of a is multi-dimensional array must have bounds for all data. So you have to at least tell the number of columns in that matrix, and then it is good to go. Now we have passed the matrix and then dimension, and then we have to calculate AR raised to power n. So, and AR we are reading in A, so basically we have to calculate a raised to power n. So the first thing, as you might have seen, we have to define an identity matrix of size n. In this case, identity matrix of size DIM. So what we have to do is basically run a loop, and then if I is equals to j, simply ij would be 1, else it would be 0. So now we have initialized an identity matrix, that is I, of size n DIM cross DIM, and if I and j are equal, basically if this cell lies on the diagonal, then we have initialized it with 1, otherwise with 0. So this is basically an identity matrix of dimension dim. After that we run a loop till n, and each time what we do, we simply multiply. We say I is equals to I into a, right? This is what we do, and simply return. But the return type is nothing, so we will leave, and we know the result is inside I because each time I is getting updated, so the result is inside I, but we want the result inside our AR array. And AR array, since we are passing AR and we are receiving in power function AR into this, that is why whatever change you made into A array would be reflected into AR array. This is how call by reference works. So since we want the result into AR not in I, so we would run a loop and then simply copy the values from matrix I to A. So basically AR would be updated and the result would be inside AR. Now the problem is matrix multiplication doesn't work like this. This is not integer, so I can write I is equals to I into A. I have to define something. I have to define, or I have to create something like this. We have to perform multiplication like we do in matrix multiplication, or instead of that we can define a multiplication function MUL, in which I can pass matrices I and A and also their dimension, indicating that okay, perform A into I. What we mean is this: perform A into I, and then whatever result is calculated, save back into I, basically update I. So we have to create a multiplication function. So return type of course would be void MUL int, let's say the first matrix to be A, and as already explained, I have to tell the dimension of a total number of columns, and then let's call it B matrix and also their dimension. Now since we have to calculate result, so we need another matrix of size dimension plus 1. The reason is so that we can have indices from 1 to dim, and we would calculate A into B and save the result into res, because we have to save the result somewhere. So that is why we are taking a matrix intermediate for saving the intermediate results. So now run a loop till dimension, and then run a loop again till dimension, and then you initialize result of ij is equals to 0. This is how matrix multiplication this is simple matrix multiplication code. And then k to dimension, result of ij plus equals a of ik multiplied with b of kj. So now all A into B, we have calculated A into B and the result is saved into res. But what we want here, when we set this, we have written the MUL function so that we can perform this, right? So what this is telling is that perform A into I and save the result back into I. So what we did there, we performed A into B, which is basically I into A. We perform A into B, but the result must be saved back into I. That is, the result must be saved back into this. So for that, we would run a loop again, I to dim, and we would simply copy the result from res, because the result is saved into this, from res to this A. Now, so what we have till now, this should work. We are just left with this print mat, void print mat in, let's call this a again, and then dimension. So to print it, this is very easy, run a loop till dimension, and then run a loop till dimension, print a of ij, and then that's all. So let's see what we did. We took three variables, t, dimension, and n. We take an input into t, that is test cases, and in each test case we are reading dimension and n. So after getting dimension, we are reading the array ar, and then we are calculating ar, which is having dimension dim raised to power n. After calculating that, we are printing that matrix. Now in the power function, we are receiving three elements in its parameter. First the array, first the matrix to which we have to calculate power n, and then its dimension. Now since the matrix is the matrix ar is matrix A is actually a square matrix with dimension dim, so we need, as we have seen, we need an identity matrix of size dim. So we are running a loop, and then we are initializing the identity matrix. And in identity matrix, if the cell lies on the dimension on the diagonal of the 2D grid, then its value is 1, otherwise it is 0. After that, we are running a loop from 1 to n, and then each time I is equals to I into a, we are performing that. For that, we have created a multiplication function which takes two matrices, multiplies them, and then save the result back into the first array. So this way I would get updated each time. So what we are doing, we are receiving a and b, two array with dimension dim. We are creating another array for saving intermediate results, and then this is basically simple two array multiplication program. You can read about it on Geeks for Geeks. So we are simply calculating the result of a and b, and after that we have to update a again. So we are running a loop, and from result copying the result into a. So that is why this would perform a into I is equals to a. And after that, since we want result into a, so while our result is into matrix I, so we are simply copying all the values from a from I to a, and now this completes our function. So let's see if we get any error, any compilation error. This is not what I suppose. So suppose we are having this much of test cases. First let's compute this. This indicates the dimension of matrix, and second one indicates we have to calculate it power 1. So if the input was 1 2 2 3, the result is 1 2 2 3, which is this matrix raised to power 1. If you take the matrix 2 and calculate its power 2, or the matrix P, say the answer is 1 1 1 1 1 2, which is right because I've already calculated this matrix. Let's calculate this matrix 0 1 and 1 1 to the power 3. The answer is 1 2 2 3, which is good because I've already calculated this matrix raised to power 3. Let's see for other test cases, and yes, so you can see there's this matrix 3 of size 3 cross 3, and we have to calculate its power 3. So the matrix is 3 3, we have to calculate its power 3, 1 0 4 1 2 2, and then 0 4 4. So the result is 17 1 1 2 16, as you 116. As you can see, the result is accurate. So this is how we write matrix multiplication. But the problem is the implementation that we did is actually m cube into n, which is expensive, of course. Now you remember, this is what we did in while we were learning binary exponentiation as well, where at that point what we did, we applied this naive approach, and then what we did, simply I already explained, we did something like this. So if you haven't seen the binary exponentiation video, just go and check, because this is exactly the code that I have explained in that video. So what we did is while n, which means while n is greater than 0, if n was odd, what we did, we updated result to be result into a and n minus minus. Otherwise we updated a to be a square and then divided n by 2 and finally return the result. So that is what we are going to do now. Instead of going linearly like this, let's comment it out. Instead of going linearly, we can simply do this. While n, if n is odd, what we have to do, we have to update I. We have to perform I is equals to I into a. So we would pass I, a and their dimension, and then n minus minus. Else we would perform a is equals to a into a with dimension din. And this is what we have to do, and we have to change nothing. So you can see we have implemented naive approach, and then we have we have gone from naive to binary exponentiation without changing much of a code. So these are two test cases I would like to test on, and this is a problem MPOW. Let me show you. Power of a matrix taken from SPOJ. So I advise you, after studying this lecture, just go and solve this problem by on your own. So we have 2 cross 2 matrix and we have to calculate it power 3, and 2 cross 2 is matrix is this 1 0 1 1. I'm not getting any result, so let me, oh yeah, I remember I made a mistake here. After this I have to do n divide equal 2. Should work now. So we have two test cases. First test case is this 1 0 1 1. The result is 1 0 3 1, which is perfect. Second test case is this 1 0 4 1 2 2 0 4 4, and the result is 17 1 1 2 16 15 blah blah blah. And as you can see, we are getting the right result. What we did, as you can see, it is very interesting, that we applied normal or naive approach, which was this. We simply initialize our identity matrix and then run a loop, updated I is equals to I into n, and then printed the result, which was actually what we were getting. And after this was naive approach, having if m is the dimension of the matrix and we have to perform n operation, so the overall complexity would be m cube into n, which is very expensive. While what we did, instead of going linearly, we applied exponentiation by squaring, or basically binary exponentiation, which would result into m cube into log n. And what we did, if n is odd, we updated I to be I into a, otherwise we updated a to be a square and simply printed the result. So I hope you have understood the matrix exponentiation, how it works, and for you this is a very simple question that you can solve. A power of matrix, where you can take a matrix of size 50 and you have to perform t test cases. In each test case, n can be as large as 10 to the power 5, and since the output can be very large, so you have to print each element modulo 10 to the power 9 plus 7. So you have to simply, wherever you are performing multiplication or addition, simply just do this and this, so you'd be good to go. I advise to solve you that problem. If you are able to solve that problem, it would be very good for you, because you have learned something new, and that is matrix exponentiation. So this was all about matrix exponentiation. In the next video I would show you how you can calculate nth element of a recurrence relation using matrix exponentiation in log n time, like calculating the nth Fibonacci number in log n time. Or there was also a problem in January lunchtime 2020. The problem was construct an array, something like that. In that also we were asked to calculate the nth number of recurrence relation. So that problem could also be solved using matrix exponentiation. So in the next video there is a lot to learn for you guys, so keep watching, and yep, thank you.